All right, so today we're going to talk about transformers. So probably which is the most important topic you should really understand. Probably this is the most important topic throughout the entire semester, entire course. So please really pay attention. Everything that we see these days in the media are basically based on transformer and diffusion model. So diffusion model we're going to cover anyway. So transformer, it's the foundation of modern NLP, and even now, even the computer vision, people mostly don't use CNNs anymore. They usually rely on something called vision transformer, VIT, which is also based on transformer, obviously. So if you understand transformer, you'll understand probably like 70 to 80% of things that are happening these days in the machine learning world, especially deep learning world. So the contents are this. So we first are going to cover what is self-attention. We previously last week we talked about RNNs and then sequence to sequence and attention. So you should really be familiar with the concept of attention already. And then we're going to expand that to self-attention. Then we're going to learn about transformer encoder side only, and then the decoder side on in the sequence to sequence subtopic. In between, we're going to talk about positional encoding, which is also an important topic. Everything is important actually today. So if you have any question while I'm going through the contents, please ask away. Raise your hand, type in the chat box, or make your voices heard, whatever. All right, so what is self-attention? Self-attention, the architecture of transformer came about in the year of 2017 by researchers, NLP researchers in Google. So they wanted to speed up translation, machine learning. So that would be NMT, neural machine translation. So prior to 2017, everybody was, all machine translation was based on RNN encoder decoder architecture. I mean, there might have been some, variations, or some even probably tried to do machine translation with 1D CNNs, but mostly it was the RNN. So it was either using LSTM or GRU and then stacking them up, putting some attention on them, and making some tricks and adding some techniques. But it was basically the fundamental structure was RNN based encoder decoder architecture. And then we've talked about the shortcomings of RNN. Either you can't put too long sequences in there, or the RNN is going to forget what happened in the past, which means that it's going to forget the first or second word in the entire sentence. So that's why we turn to bidirectional RNN. But then if you think about it, you can use bidirectional RNN on the encoder side, but you can't do that on the decoder side, right? So there's a shortcoming. And then basically, you need to run a for loop on the encoder side and in the decoder side as well. So it's, like the entire thing requires a for loop, which means that if you put a long sentence translate into the RNN model, it's going to get slower and slower. It's going the computational complexity would be, of course, proportional to the length of the sequence. So those shortcomings were probably bugging the Google researchers, because they were providing services for machine translation throughout the entire world with as many languages as possible. They probably service for like at least 100 different languages or so, maybe 50 to 100. I'm not really sure, but anyway, so every single day they are providing machine translation services, and those shortcomings were really bothering them. Especially the for loop. So when this paper, Attention is All You Need, which is a transform paper, when it first came out, one of the contributions the authors were claiming is the speed, because you no longer need to, with transform, you no longer need to run a for loop to input to feed a sentence into the architecture, as opposed to RNN, where you have to put one word at a time, one word after another, after another, after another. Here you put all the words, all the tokens into the encoder at the same time, and everything is just parallelly processed, which is actually what GPU does really well, and Google has a lot of GPUs. So yeah, the core concept is let's use only attentions to handle sequences. That's the fundamental, the core idea. So how do we do it? How do we let the model know that it is given a sequence without actually running a for loop? When we put all the tokens together, then it might look like a set, like a set of items or set of tokens or set of words, right? It's just a bunch of stuff given to the model. So how do we let the model know that it's not just a bunch of stuff, but it's actually a sequence? There's a concept of order among one another, among one tokens to among all tokens, basically. So their idea is let's use attention, and how the authors of the transform paper did is they use attention like this. So first, I is the main character. I is the so-called the protagonist, if you will. So I is the main character, and then in the I's perspective, it takes a look at its neighbors. So right to the right, to the one step right, there's another token, which is like, and then another step to the right, there's going, to, movies, and termination symbol. So at least I know the word token. The token I know is that there are 5 things to the right. Then it's like's turn. So like is the main character, and then like takes the token like takes a look around at around the neighborhood, and then we see that like C said there's I in the left and going to, movies, and end on the right. So now like also knows what's happening around itself, right? So this goes on for all the tokens, all the words. So going takes a turn, then to takes a turn, movies takes a turn, and then end takes a turn. So every single word takes a turn, takes a look around the neighborhood, and then understands what's happening in the neighborhood, in the left and to the right. And since all tokens do that, then that means the model knows what's happening in this set of items or in this set of words. And then there's it's a sequence, because every word takes a turn and then understands or recognizes what's happening in the left and what's happening on the right, right? So that's the core concept. So in a more mathematical form, what's really happening in self-attention is this. So this is the so-called QKV operation, or scale dot product. So there's Q and K and V, which is the core. So this is called query. This is called query. This is called key, and you know there's a transpose here, and this is called a value. So there's query key value, and we're going to talk about this. But query key values are derived from the words, from the input tokens, and the query key value, they're all matrices. So you can see the capital letter, uppercase letter, QKV. And when you do QK transpose divided by square root of D is the size of the matrix, actually the dimensionality of the rows of the matrix. So query is a matrix, key is a matrix, value is a matrix. Then each, for example, in the key, there's a single vector. And this vector there's a size of the vector, which is, let's, for example, say that this is 128, for example, 120 dimensional. Then D becomes 128. So basically, D is just a normalizing factor. And you have the softmax and V. So everything before the V, right here, yields this matrix, which is actually the size of the matrix is exactly the same as the number of words. There's I like going to, movies, and, which are 6 words. Then it's a 6 by 6 matrix. That's what softmax QK transpose divided by square root of D is. It's a 6 by 6 matrix filled with numbers. And you can see that each row sums up to 1. That's why softmax is there, because softmax normalizes row-wise. So let's look at the numbers one at a time. What's the first number mean? What does this mean? This 0.5 means it's how the first word I, I'm going to erase all this, is how first word I thinks about itself. It's the compatibility between I and I itself. Second number, 0.1, this is how I thinks about like. It's the compatibility between I and like. So I said that before, each word takes turn. So each row is the term. It's how when I is the main character, how it thinks about itself, its neighbors. So like is like I and like compatibility, like 10%. Then I and going 0%, I and 2, 20%, 20%, 0%. Second row is when like is the main character. And the first number, 0.2, means like and I. So like to the left, when like considers I, it likes the compatibility or the affinity. For example, like we can think about it as like a friendship or affinity or compatibility, something like that. Basically, it's 20%. Then when like considers itself, it's 60%, and then 0.0%, then 20% for like and movies, and 0% for determination symbol. This goes on for all the words, and these are just made up numbers. This entire thing is I just made it up, so it doesn't, it's not as, it's just, you can think of it as just imaginary, like, imagined numbers. So when you have this matrix of affinity or this is basically attention distribution. You can see that for each row, it's an attention distribution, like the one that we've seen in the previous Tuesday lecture. So you have the attention map. This is called attention map, or attention matrix, attention map or attention matrix. So once you have the attention matrix, what you do with it is you multiply with the value vector. You can see that it's V is a vector. V is a vector because each row is a word embedding or token embedding. So when you have the attention matrix, you multiply it with the V matrix, the value matrix. And what happens is that it's obviously you're going to have a inner product between this inner product here, and you get this one. Inner product between, all right. Inner product between the second row and the value, then you get this, right? Like this. And the inner product between the third row and the value, and then you get this, right? So let's see what happens in the first row of the final outcome. And this, you can see here is, as you can see, it's a weighted sum. It's a 0.5, 50% I plus 10% like plus 20% 2, 20% movies, because those are the non-zero cells in the attention map. Second row is the same. It's 20% I, 60% like, and 20% movies. So what's happened here is that if you only look at the first row here and here, what's happened is that before the weighted sum, I was by itself. It was pure. It was just one token, which was I. And then when you do the operation, what you have is 50%. So the purity has decreased to 50%. And then the rest is filled with its neighbors. So it's basically tainting itself or corrupting itself to get mixed up with its neighbors. So that's what we call a contextualizing, because I is now considering its neighbors 20%, 10%, 20%, 20%. So it's looking at its context and then it's mixing it up to get more contextualized or mixed up representation, which is the same for the second row, third row, fourth row, fifth row, sixth row. So that's what self-attention is. Self-attention is where each word takes a look around its neighbors and then sees what it likes, decides which word, which neighbor it likes, and then that's what the attention value becomes. And then you mix them up, and then you have a mixed up or contextualized outcome. Right. Any question? So this is it. This is basically it. This is the whole concept of transformer. Because rest of the transformer is just, it's just feed forward layer on top of the self-attention, and then some tricks to make it train faster with layer normalization and and the skip connections and all that. So this is the most important concept. Right, so if you visualize it, this is what happens in the QKV operation. Let's assume that you have only two tokens, which are thinking machines. By the way, I borrowed this this figure from this awesome blog. So if you want to see an animation, then you should definitely visit this blog. So let's assume that you have only two tokens given to your model, and then you're trying to do a self-attention, which is basically this. Then you have a word embeddings or token embeddings, which let's assume are just four-dimensional. And then, as I said, Q and K and V, the queries and the query, the key, the value matrices are derived from the input words. So that's what's happening here. You have something called WQ, WK, WV, which are the learnable matrices. They are the trainable parameters, basically. So you multiply K, X1, I'm sorry, you multiply X1 with WQ, and that's what this is what you get here. So it's basically, it's 4 by 3. So it's X1, 1 by 4. This X1 transpose WQ probably, right? That's what you get here, Q1. And X2 transpose WQ, you get Q2, right? The same thing for K1, K2, V1, V2. And this, you need to make it really clear that these are different learnable parameters. WQ, WK, WV, they're different separate parameters. So you have separate sets of Qs and Ks and Vs, basically. And what happens is that so this is thinking's turn. This is where thinking becomes the main character and then considers its neighbor. So when you're considering the neighbor, you fix the Q, which is the querying token, and then you consider how compatible how compatible the Q1 is to other keys. So how compatible am I to this K1, which is the self-compatibility, and how compatible is thinking compared to machines, which is K2. So Q1 K1 inner product score 112, Q1 K2 inner product score becomes 96 points. So there's 112 points for itself and 96 points for thinking to machines. And then since this inner product scores could be arbitrarily large when your vector becomes large, when this is like, I don't know, like million size vector or trillion size vector, that your inner product score basically can increase as your vector size increases, right? So we don't want that happening. So that's why we divide by square root of D. So in the original paper, in the original attention is all you need paper, the query key value, their dimensionality was 64. So square root of 64 is 8. So that's why you divide by 8. So divide by 8, you get 14 divided by 8, you get 12. So now it's 14, 12, and then you do a softmax. You put a softmax on top of them. So softmax of 14, 12 becomes 0.88 and 0.12. So you have 88% compatibility with yourself and 12% compatibility with machines. So that's what happens when thinking is the main character. And probably you can do the same thing with when machine is the main character. You'd set Q2 and then compare between itself and its neighbor. So once you have 88% and 12% attention distribution or compatibility distribution, you basically you weight sum the values according to it. So V1 and V2, and you can see the V2 is very opaque, it's almost transparent because there's only 12%, 12% a weight applied to V2. So that's where 0.88 times V1 plus 0.12 times V2 gives you Z1, which is this. And in the same manner, you can get Z2 when machine is the main character. Right. So far, it seems like we're taking turns. We're taking, like, one word is the main character, another word becomes the main character, the third token becomes the main character, and every single time you calculate Z1, Z2, Z3, Z4, Z5, and it seems like you are running a for loop, which we try to avoid in the first place because RNNs require for loop, and that's what Google researchers didn't like about one of the things that the Google researchers didn't like about RNNs. So that's the whole thing about this transformer is no required for loops. But here it seems like we're doing a for loop. So let's change that. Is like this. Instead of actually taking turns, you just do it all simultaneously at the same time using a matrix vectorized form. So there's first word x1, x2. You just do it in one go. You just multiply x1, x2 which is basically x, your input tokens. Multiply with WQ, you get two Qs, Q1 and Q2. Same for K1 and K2, same for V1 and V2. So you no longer need to take turns to calculate Q. You no longer need to calculate this one and this one separately. You just do it all in one go. And then 2KV operation is the same. You don't do this first and then this second. You don't do that. You just take everything in a matrixized form, and then just you get Z1 and Z2 in one go. So you can see what's happening here, right? This is Q1, Q2, K1, K1, K2. This is V1, V2. You do this exact same thing, and then you follow this exact formula, and you get Z1 and Z2. So no for loops involved whatsoever. Everything is just parallel. If you have a powerful GPU, this will be really, really fast compared to how RNN can take up a long time. Right. So yeah, this is just a recap. So you understand what's happening here, right, underneath the hood. So that's self-attention. Now we're going to expand it to multi-head attention. So this is actually one of the things that were really interesting in transformer. So what is multi-head attention? What if you use two attention matrices, two attention maps instead of one? So before we had only one QKV operation. So this is softmax Q K transpose divided by square root of D. This was V. So this is one set of QKV operation in the first matrix and first V, and then you get first Z, right? This is first Z, this is Z. But what if you had another matrix, another attention matrix, again, here, with different distributions and different values in the final different values. So this would be like Z1, this could be Z2. There could be like more, Z3, Z4, Z5, and you must understand that each matrix, each attention matrix should have different values. So that's what we mean by that is that even for a single, when I is the main character and then considers itself and its neighbors, maybe we give it another chance for it to become the main character, and then maybe consider different proportion, different ratio. Like maybe this time only 40% for itself, 20% for like, and 10% for going, 10% for two, 0% for movies, and so on and so forth. Maybe in order to understand language, we need more than just one attention matrix, more than one weighted sum. So that's basically the motivation behind multiple self-attention or multi-head attention. So multi-head attention is you can imagine how we can extend a single head attention to multi-head attention. You just use different QKV matrices. So there's WQ0, WK0, 0. So this is the first set of learnable parameters for the first head or first attention, self-attention. This is the second set of matrices, WQ1, WK1, WV1, for you to compute the second attention matrix and the second QKV operation. So as many times as you want. If you want to do like 3 self-attention or 5 self-attention, you just need to add more sets of WQKV, WQKV, WQKV. But that means that larger number of learnable parameters. So you're basically increasing the capacity of the model. But modern transformers actually just, have a fixed upper bound. Like I'm going to use maybe 128 and 128 dimensions for self-attention. And then if you use 2 attention heads, then it's 64 each. If you use 4 attention heads, then it's 32. If you use 16 attention heads, if you use 8 attention heads, then it's like 16. It's basically you divide or you distribute your fixed amount of resources across different number of attention heads. So in modern transformers, you don't actually increase the capacity, but you increase the channel basically. Anyway, the number of self-attention heads or number of multi-head attention is up to you. It's a hyperparameter basically. So, but in the very first transformer, in the original transformer back in 2017, they didn't actually set an upper bound and distribute it to a different number of heads. They actually just increased the number of learnable parameters. So they had to actually gather it. So because, for example, in our original example, it was every Z was three-dimensional had a three-dimensional output, right? So first attention head, first set of self-attention would give you Z1, Z2, which are both three-dimensional. Another head, all the way to total 8 heads. because in the original transformer paper, they used 8 heads. So there's 8 sets of Z's basically. And since it's larger than your original intention, you have to actually concatenate them and then downsize them by using another compression matrix, basically another linear operation, basically with a pretty large learnable weight matrix. So this is another trainable matrix, so that you can downsize it to the original size, which was 4. So you can see that it's 4 dimension here. So you want to downsize it to 4 dimension. So you want your input and out to be the exact same size when you're using transformer. So these days it's a little bit different. If you look at the Hugging Face code and the canonical transformer code, it doesn't work like this, but conceptually in the very first paper it worked exactly like this. So you gather all the outputs from your self-attention heads, 8 heads in total, 8 heads, and then you concatenate them like this horizontally, and then you compress them with a single linear operation to the original size. All right, so this is the whole picture. So you have assuming still you're given 2 tokens, thinking and machines. So this is X1, X2. You have 8 heads. So there's a single channel here, total 8 channels. You have 8 outputs, and then you compress it with a linear operation, and then you get Z, which is the final output, which is the same as here, same. Right. So you can imagine what are the learnable parameters in the self-attention. It is here, this is one learnable parameter, WO, which is the compression linear operation. And then there's 8 sets of learnable parameters, WQKV, WQKV, WQKV. Right. So what is it good for? What does it really help? Multi-head attention, does it really help? So this is a visualization for you to understand what's really going on. So you can see that the layer number is 5, which means that there's layer 0, layer 1, 2, 3, 4, 5. This is in the original transformer paper. The transformer paper was intended for was aiming at translation, machine translation. So it had an encoder-decoder architecture, and there was 6 layers. So the encoder consisted of 6 layers. So there's 0, 1, 2, 3, 4, 5. So it means that we're looking at the last layer of the encoder. And then you can see there's 8 colors, 1, 2, 3, 4, 5, 6, 7, 8, which means that it is using 8 heads. So each layer, there would be 8 heads. First 0 layer, 1 layer, second layer, third, like layer 0, layer 1, layer 2, all the to the layer 5. Every single layer uses 8 attention heads. And here we're looking at 8 attention heads in the final layer. And especially among the 8 heads, we're looking at the second attention head, the orange. So you can see the orange color here, right? Let's look at what's happening. I think the entire transformer model was trained for translation. So this is the attention function that was fine-tuned for or trained for translation, maximizing the translation performance, right? So look at read the entire sentence. The animal didn't cross the street because it was too tired, and we're looking at when it is the main character. So this is when it's being the quarry. It is being the quarry, and it's looking at all the different keys, which are all these different tokens, right? Including itself. So you can see the strength of the attention, and look at here. The strongest tie or strongest connection between the quarry, it, and the case are here, the animal. So this is the strongest connection. This is the strongest compatibility. It means that it and the animal, they are actually, what's happening here is that if you read the sentence, it is actually the animal. It is a pronoun. it's 그 대명사죠. 있으면 대명사고, 대명사는 이제 그 지칭하는 바가 있을 거잖아요. 그게 바로 그 동물이죠. 그 동물이 길을 건너지 않았다. 왜냐하면 그것은 너무 피곤했으니까. 근데 이제 그것이 바로 그 동물 그 자체니까, 지금 보시면은 지금 여기가 가장 이제 어텐션이 세다는 거는 대명사의 정체를 파악하고 있는 이제 대명사 해석 또는 coreference resolution을 하고 있는 거죠. 이제 요 헤드, 두 번째 헤드는 coreference resolution, 대명사 해석을 하고 있다라고 보시면 됩니다. So as I was saying in Korean, the second head of all 8 heads, the second head's role is, the purpose of second head is to resolve the identity of a pronoun, it, right? Well, there are some Are there any other pronouns? Yeah, there's no other pronoun, but at least we can assume that the second head is responsible for resolving the identity of a pronoun. What about the third head, the green head? You can see now it's the attention distribution is totally different. The first attention distribution, this was where the mode was. It was like this, right? But the second attention distribution, it's like this, right? And you can see tired is the strongest connection between it and tired. And now we can see what's happening here. It is tired. It means that in this clause, this is nested form, right? There's first sentence and second sentence connected by the conjunction because. So you can see this is the second part. And in the second part, there's always a subject and a predicate. Subject and predicate. So this is the predicate. So the third head is what actually it is doing is it's resolving a predicate for the subject it. 그러니까 이제 주어 동사 또는 주어 서술어의 관계를 해소하고 있는 거죠. 그러니까 얘는 여기 절 안에서는 얘가 주어고 이게 서술어니까 이제 서술어 쪽을 가리키고 있다. third head, 세 번째 attention에 대해서는 이렇게 파악을 하시면 되겠습니다. So you can see that each head is actually serving a completely different purposes. Like some head is responsible for coreference resolution, and another head is responsible for resolving subject predicate relationship. And you can see if you turn on all the heads, then you can see it's there's very diverse set of distributions. Any questions so far? No? Right. So now we move on to transformers. So prior to this, up to now, everything was just purely self-attention, but transformer is more than self-attention. I mean, self-attention is probably the most important idea in transformer, but other things are also important. So as I said, transformer was proposed to perform machine translation. So assuming that this is French to English, so there's encoder, encoder accepts French sentence, decoder generates an English sentence. And as I said, the original paper consists of 6 layers in each side. So 6 layers in the encoder, 6 layers on the decoder, and each encoder is exactly the same. It's just a copy and paste. And so are the decoders. Decoder are it's the mathematical formula is exactly the same. It's just copy pasted with different sets of learnable parameters, and that's it. And you can see that the final layers output, there should be final layer output. If you are following my lecture pretty closely, you can see that the input and the output, the number of input tokens and the number of output tokens for a single encoder is exactly the same. 3 words in, 3 words out, or tokens, 3 tokens in, 3 tokens out, because we had 1 Z for 1 X, right? X became, so actually maybe this is wrong direction. We had 1 X becoming 1 Z, X2 becoming Z2, X3 becoming Z3, right? So this is exactly that. You have the same number of input tokens as the number of output tokens. And those output tokens will be somehow plugged in or sent to the decoders, every single layer decoder. We'll see how it happens. Right. As I said, we're going to look at the encoder first, and then within the encoder, we just need to look at one layer or one block, because all the other blocks are exactly just copy pasted. So single block looks like this. So there's 3 words going in, 3 tokens going in, and then it first goes through the self-attention, which is exactly the softmax Q K transpose square root of D times V. This is just that's it, self-attention, that's it. And then you have Z1, Z2, Z3 output, and then you put it through a feed-forward network just to massage it a little bit further. Because if you think about the self-attention, everything is just linear. All the operations were linear operations, except for the softmax, but that was for normalizing purposes, right? So everything was linear. So you need some nonlinear operations to make it really powerful, right? So that's where feed-forward comes in. So actually, each feed-forward, so it's not just one single feed-forward taking, like one gigantic feed-forward network taking 3 tokens and then spitting out 3 tokens. No, that's not it. We just have a feed-forward layer, feed-forward network that is applied independently to all the tokens, like here, here, here. So this looks like this, like Z1, Z2, separately being fed into the feed-forward network, and then finally giving us some final output. We're going to call it R1 and R2. So self-attention is a joint operation. It looks at self-attention layer, looks at all the tokens given to itself, and then mix and match, basically mixing it up, contextualizing. But in the feed-forward layer is separate operations for each token, separate. So there's a big difference between the two. And as I said, there's some stuff that helps the model optimize, helps the optimization process a bit smoother, which are add and normalize here. So we've seen self-attention, we've seen separate feed-forward, independent feed-forward layer, and then in between them, there is add and normalize and add and normalize. And this has nothing, there's no learnable parameters here. It's just, actually, yeah, normalization would probably require some scaling factors, but basically it's not, compared to feed-forward and self-attention, this is not this is not directly involved in the training, performing the translation test, basically. So add and normalize. So why do we say add? Add is because there's skip connection. So here before going into self-attention, there's a skip connection here, and after the self-attention, there's a skip connection with a layer normalization. And then before going to the feed-forward, there's another skip connection, and then there's normalization layer. So that's it. So these are just to smooth, just to ease to help the optimization process. And we've learned layer normalization, right? So we talked about batch normalization when we were talking about CNNs in the 7th week or 6th week, right? So no need to talk about layer normalization. There's one red box, which is also very important, which is positional encoding, which we will discuss later. You can see that positional encoding is applied to X1 and X2, all the tokens, before the tokens are actually fed into the self-attention. So we're going to talk about this later. So all in all, the entire thing looks exactly like this. So thinking machines, 2 tokens in, there's positional encoding, slightly modified color. You can see that this was kind of like thick green. This is a little bit light green because of positional encoding. And then self-attention gives you the same number of Z1 and Z2. There's layer norm and add and norm. So add and norm. So you can see that X is being connected via skip connection. So X plus Z layer norm. And then you have a slightly different colored Z. You can see the color difference here. Slightly different color, Z1, Z2, fed into the feed-forward, add and normalize again, and then you get final R1 and R2. And then you can repeat this process because, as you've seen here, it's just 6 encoders. So X1 and X2 going in, R1 and R2, R1 and R2, R1 and R2, all the way to the final R1 and R2. So that's what's happening here. So at least you need a for loop here, right? First loop, second, third, fourth, fifth, fifth. So at least there's a for loop across different layers, but within the sequence, within the tokens, there's no for loop. Right, so that was basically the whole architecture of encoder. You can see it's pretty straightforward. As long as you understand self-attention, the other are just auxiliary stuff. I said we're going to talk about positional encoding. So if you have a keen observation, I said that when we put all the tokens in the very first beginning of this class today, I said that when you put a bunch of stuff at the same time as like a bunch of set of tokens or bunch of tokens into the model, I said that we wanted the model to understand that it's a sequence, not just a set of stuff. But if you followed me so carefully so far, then you would see that it is still treating, the self-attention is still treating its input tokens as a set of tokens, not a sequence of tokens, because there's no concept of order here. What I mean by that is, if you imagine, what if you put, so the current sequence of order is I like going to movies end symbol, right? This is the current sequence. But what if you put like I going to movies end symbol? What happens if you put this instead of this? What would happen is the rows will change places. Like this row would go here and this row would go here, right? and this row would go here, and this row go here. Same, this row will go here, and this row would go here. So the rows will change places, but that's it. The contents doesn't change. For the 0.5, 50% I, 10% like, 20%, 20% movie, they will go here, but their proportion, their ratio, their weighted sum wouldn't change. It's just changing the place, changing the rows, and that's it. The contents wouldn't change. And that could be a problem because if you think about the language, you are, okay, I'm just going to erase everything here. You are a girl, termination, and are you a girl, termination. So these two are very, very different sentences. This is just statement. This is a question, right? One is a statement, one is a question. So their contents should change. It is just changing positions is not enough. It's insufficient. You want the inside, the contents to actually change to reflect the fact that now it's a question rather than a statement. So there's there's like different semantics involved, right? But that doesn't happen because there's no concept of order in self-attention. It's basically set encoding rather than a sequence encoding. So not a sequence, it's a set encoding. So far, everything clear? This is a very important concept because this is a very strong connection to graph neural networks and all the modern, set encoding and all those stuff. So, and that is why transformers self-attention is such a powerful model because it doesn't assume anything. If you use it as just vanilla self-attention, you don't assume anything. No, you don't assume any relationship among the tokens. You don't assume there's a sequence. You don't assume there's like a size difference. Everything is just given to the self-attention as is, and then it needs to figure out the relationship in a purely data-driven manner with millions or trillions of data. That is why transformer is such a powerful model, but also requires very large number of data set. Very large number of training samples to figure out so that it can figure out the intricate, all the relationship between the tokens basically. But what we want to do here is we want to enforce the model to treat them as a sequence. We want to constrain the hypothesis space. We want to let the model know that you're dealing with a sequence, so act like it. Like you don't need to assume that it's completely arbitrary. There's a certain order among the tokens. So we want to enforce that information onto the self-attention. So how do we do it? That's where position encoding comes in. So we need to inject order information to let it understand that it's dealing with a sequence. So what really happens is when you put your input tokens, you actually add your input tokens to something called positional encoding. So positional, they're also vectors, they're embeddings. So positional encodings, T1, T2, T3, representing each position. T1 representing the first position, second position, third position. You add X1, you add X1, T1, you get slightly different X1, slightly different X2, slightly different X3. And then the rest happens with the encoders and the self-attention feed-forward network and all that. Right, so how do we invent something called position encoding? Like what kind of properties do we want out of positional encoding? We want things like very, very natural stuff, It should like output a unique encoding for each time step, So, and distance between any two time steps should be consistent across sentences with different lengths. For example, like if you're dealing with five tokens, then the distance between the first token and the second token should be the same as the distance between third token and fourth token. Like everything should be regular, basically. And model should generalize to longer sentences without any effort. So if your model was dealing with maximum 5 tokens during the training stage, and then in the inference stage or the test stage, you want to be able to give the model 6 tokens or 7 tokens without any problem, no problem at all, as long as this positional encoding is involved. And it must be deterministic. These are all, very, very natural, natural desirable properties you want out of positional encoding. But if you use a very naive approach, for example, you just simply give one scalar value for each position. First position is given 1, and then you somehow concatenate 1 to your X1. and then concatenate 2 to your x2, or maybe you put 1 through some feed-forward network and then you make it into a vector or something like this. So this could be the very, very, very naive, straightforward solution to having to come up with a positional indicator. So this is strategy number 1. This could be another strategy. Strategy number 2 is, well, at least you want the maximum size to be 1 all the time, regardless of how long your sequence is. For example, if you took first strategy and you have 1, 2, 3, 4, 5, 6, 7, that was during your training, but when you're testing, suppose that you were given 8 token sentence for the first time. So you will see, the model will see the number 8 for the first time. So it's not ready to deal with 8. So this kind of like out of distribution, right? So we don't want that to happen. So in strategy number 2, what we do is we set the maximum value for your positional encoding, which is 1, and then you divide by the number of tokens in your sentence to assign different values to each time step. So 0.14, 28, 42, 56, 70, 84, 100. But this also is problematic when you increase when you give a longer sequence than in the test phase than all the training samples, which is that this part is okay because you're still this number 1 is what the model has seen during training. But the problem is that now 84 has become 87, 70 has become 75. It's slightly changing, slightly changing. So it's still not a perfectly satisfactory strategy. Like both S1 and S2, not the perfect strategy. If you think of, so there's a bit, if you're being clever, you can actually deal with not scalar values. These are all scalar values, right? Instead of handling scalar values, you can actually use vectorized form for your positional encoding, which is, in this case, you're using binary values with 4 dimensions. So 0, the first token will get 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, so on and so forth. So this looks nice. But the problem is that in order to cover 15 tokens, you needed 4 dimensions, basically 4 bits. So this is very much a waste of space, because we're using binary values. So this is not also satisfactory. But but what Google researchers actually came up with is very clever. If you look at each dimension, you can see that the red numbers change its values very frequently. It's 0, 1, 0, 1, 0, 0, 0, 1. But if you look at the second dimension here, you can see that the blue values, the blue numbers, don't change values as frequently as the red. It's just 0, 0, 1, 1, 0, 0, 1, 1. Then when you go to the third dimension, it's 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1. And then the yellow is all 0, all 1. So you can see that the frequency is different between different dimensions. So that's where we can extend this binary formed positional encoding into the continuous form using sine and cosine values, sine and cosine functions, basically. Using sinusoidal functions, you can apply different frequencies for each dimension with continuous function, like sine and cosine functions. So that's what's actually happening here. It's 128 dimensional vector, 128 dimensional position encoding, and then there's position 0 all the way to position 50, And you can see that first dimension changes its values very frequently. It's like 1 to -1, so very frequently. But when you come to here around here, it's like 0, 1, -1, like something like this. Basically the frequency is not as high as in the first dimension. And if you go to here, you can see the value is barely changing. It doesn't even reach 1, I think. So you can see this is the extension. This is the continuous extension of this binary value. So that's what Google researchers came up with when they were designing a positional encoding function. So the exact function looks like this. They actually interchange between sine and cosine, sine and cosine, sine and cosine with the same frequency for for a pair of sine and cosine. So same frequency, all the way to the final dimension. And these are just carefully chosen hyperparameters. So when you are you won't have to design positional encoding yourself, because when you use Hugging Face or any PyTorch library, you will just call a PyTorch function, positional encoding function or sinusoidal function, PE positional encoding function. And then you can just put your position like 5 or 10 or 15, 100, whatever. And then it'll give you back a corresponding vector v. Could be 120 vector like this, could be 256 vector, whatever. It's a hyperparameter. All right, so far we've looked at transformers, self-attention, encoder, and the positional encoding, but I would like to just note that there are different ways to handle sequences, and they're all aiming for the same thing. If you think about RNNs, you put the tokens, and then you get the corresponding number of hidden layers, right? That's what you can do with RNN. If you use 1D CNN, you can do exactly the same thing with proper padding. Proper padding, you put the number of tokens, you get the same fibers or same number of feature maps, like feature maps in the CNN. With transformer, it's the same thing. You put the number of input tokens, you get the same number of output tokens. These would be called what we call a contextualized vectors. So they're all serving the same purposes. Either use RNN, 1D CNN, transformers, or any other sequence handlers, sequence encoders. You would be doing the exact same thing. It's just that RNNs and CNNs and transformers have different assumptions they have different inductive biases, basically. RNNs have a very strong enforcing of sequence, the order. CNNs assume that there are local dependencies. Transformer doesn't assume anything. That's the power of transformer. Also, kind of like weakness of transformer, because it requires a lot of training samples. But if you have infinite number of samples, then probably transformer is the way to go. All right, so finally, we are going to sequence. So far, we've only looked at encoder, right? So we've only looked at this part and how each layer looks like with the self-attention and feed-forward and the add and normalize and positional encoding here, right? So we're going to the decoder part now. Yeah, this is just a recap. So decoder is a bit more involved than encoder. So decoder, there are 2 attention layers instead of 1. In the encoder, we had one self-attention, then there was feed-forward, and that was it, right? In the decoder, there's something called masked self-attention, and then there's something called encoder-decoder attention. So there are 2 attentions, and then the rest is the same. They're just add and normalize, feed-forward. These are exactly the same. So why are there 2 attention modules, 2 attention layers inside a single decoder? Which is pretty easy to understand. If you think about the encoder's output, there will be R1 and R2, right? There will be R1, there will be R2. And somehow you need to use them in order to translate, because translation, you translate a given sentence into another language. So this is your given language, given sentence. This is your, well, it was actually, we were talking about French to English, but in this case, this is thinking machines. I mean, please excuse the ever-changing example, but still, we're doing a translation basically. So in order to do translation, you need to consider what's happening in the encoder side. So you need to put them in somehow into the decoder, and that's where encoder-decoder attention, and that's what encoder-decoder attention is for. You put R1 and R2 into the decoder through this channel, through something called encoder-decoder attention. Then what does masked self-attention do? What this does is, decoder is basically a generator. Decoder is a conditional generator. It generates English, or it generates a output sentence conditioned on the input sentence, right? So this is where conditioning happens. This is where generation happens. When you're generating your output sequence, output sentence, you need to be really careful not to cheat and look at the future tokens, right? So that's where masked self-attention, we'll talk about this basically. So we'll talk about each of them actually separately. So decoding process. So let's assume that you're translating your French sentence into an English sentence. So this is your R1, R2, R3, and you're ready to go. So you have a decoder, and then linear softmax is just for a softmax layer for determining which word you want to predict for each time step in the output sentence, right? So first, you have R1 and R2, R1, R2, R3. You convert them into keys. You convert them into keys and then values. So that's where you need keys and values because we're going to look at the encoder-decoder attention. So encoder-decoder attention is where encoder's output serves as keys and values, and decoder's input, so the decoder's input would be coming from here, serves as queries. So you have keys and values from the R1 and R2, R3, and then you have a hidden start symbol. Like, we took a look at the RNN sequence encoder-decoder architecture. There was a start, and then you start generating a corresponding translated sentence, right? So there's a start symbol, and then you go. And so given a start symbol, you hopefully you would predict I, which is because Jesui Judyang is I am a student. So so start with considering K's and V's, you generate I. And then in the second step, with I given, you can generate M. With M given, you hopefully can generate A to student to the termination symbol. So that's when you end your translation. Only when you see end of sentence, only when your generator generates end of sentence symbol, that's when you know you need to stop generating or translating. Oh, actually, there's a question. Question from 전소영. 교수님, 사이너소이드 펑션 포지션 인코딩 값을 인풋 토큰이 각청에 더하는 건지 인풋 토큰을. 네. 원래는 더하는 걸로 되어 있습니다. 이제 오리지널 그 페이퍼에서는 여기 안 나오네. 네. 이렇게 더하는 걸로 나와 있죠. 더하는 걸로 돼 있습니다. 그러니까 컨캣을 해도 상관없어요. 근데 컨캣을 하면 또 차원이 늘어나니까 이제 얘가 지금 이미 뭐 예를 들어서 지금 128차원이면 얘도 뭐 128차원이라 치면 더하면 이제 그냥 128로 끝나는데 이제 컨캣 해버리면 256이 되니까 뭐 그렇다고 그러면 이제 얘를 일부러 뭐 32차원만 써가지고 컨캣한다. 뭐 그래도 돼요. 사실 뭘 해도 상관없습니다. 어떻게 하든 결국은 다 배우게 될 거예요, 트랜스포머. 근데 오리지널 리서치에서는 이제 둘이 같은 차원을 놓고 더해가지고 이제 가는 걸로 더해가지고 진행하는 걸로 되고요. 나중에는 이제 이거를 지금 이제 이 디터미니스틱 펑션으로 이제 배우잖아요. 지금 요런 펑션을 통해서 이제 얘네들이 결정되는데 나중에는 그냥 각 토큰마다 이거를 그냥 러너블 파라미터로 놓고서 각 차원의 포지셔널 인베딩을 러너블 파라미터로 놓고 걔네들 학습하는 식으로도 많이 합니다. 이제 당연히 그러면은 학습할 때 봤던 사이즈 이상의 이 시퀀스가 들어오면 테스트에 그럼 이제 그때는 해결을 못 하겠지만 애초에 그냥 학습할 때부터 넉넉하게 뭐 한 8,000 정도를 그냥 가지고 학습을 해놓으면은 그러니까 예를 들어서 나는 테스트 때 절대로 8,000 이상을 볼 일이 없다. 그럼 트레이닝 때부터 미리 8,000 딱 잡아놓고 하면 되거든요. 그래서 그런 식으로도 많이 합니다. 네, 일단 원래는 더한 걸로 돼 있다. 네. Right, so we've took a look at the entire sequence of process of generating the corresponding translated output. So that's, and as I said, this is where you need encoder-decoder attention. So encoder, we're going to skip the prediction layer. So encoder-decoder attention. This is originally in the encoder side. What really happened in the encoder's self-attention layer is that each token supposedly, like imagine that each token took a turn becoming a main character and then looking at its neighbors and then calculating the compatibility or the attention distribution across all the neighbors and the weight summing it. And that was what the encoder's attention layer was, right? In the encoder-decoder attention, what happens is that for example, let's say that it's time to predict the first token I. So we are given a start decoder. The decoder is only given a start and we want to predict I for the first time. And what happens is that we already have K's and V's derived from R1, R2, and R3, right? Then start token becomes a Q. Start becomes a Q and then calculates a compatibility between Q, which is start, and R1, R2, and R3 using Q, K. Using Q and K. Using Q and K, you can have a start R1, R2, like R1, like 0.3, 0.2, 0.5, something like this, basically. Like because there's only R1 and R2 and R3. So compatibility or the attention distribution across all the R's. When start is the Q, then based on that, you do a multiplication between this attention matrix or attention vector with a value which is also derived from R1 and R2 and R3, right? So that's what happens in the encoder-decoder attention. So each time, so this is what happens when start is the main character, but then you can assume that when I is the main character, so start is already used up when we were predicting I. So now it's I's turn to predict M, right? So in that case, I becomes the key, I becomes the query. So I becomes the query, and then also again calculates a similar attention distribution between I and R1 and R2 and R3, right? R1, R2, R3, and then multiply this V. So you can see what's happening. There was start before I, which was also attention matrix, attention value, attention vector. With I, then there should be I am a student. So they all should take a turn and become a Q. So you can assume that what's happening is there's I am each time having a attention vector. So basically it's a inside what's happening inside the encoder decoder attention is you have a attention matrix where the number of rows are the same as the number of input tokens on the decoder side, but the number of columns is the same as the number of output from the encoder side. So that's what happens with the attention matrix in the encoder decoder attention. And then you multiply with a value matrix which is derived from R1, R2, and R3. So that's what happens in the encoder decoder attention. Right. So using that, you have encoder decoder attention layer here, and then you pass it through a feed-forward network, and then you do it for all the different layers of decoders, and then finally you can basically you can actually I need to blow it up. So there's start, there's I, there's M, there's a student. Yeah, that's it, right? That's start I am a student, right? Start I am a student. And then, for example, in this time, this I is because I is the query. So I is query. So you have a V, you have a weighted sum V derived from this I, right? And then you pass it through a feed-forward network, and then you do it for all the decoders, and then you will have. Let's assume that you get S, because output of the encoder was R. So let's assume that you have output from the decoder, which is S1, S2, S3, S4, S5, and S2 is used to predict M. S1 is used to predict I. S3 is used to predict A. S4 is used to predict student. S5 is used to predict termination symbol. Right? So that's it. Like S1, you push it through a softmax layer and then predict I. When you put I in, you push it through you will have S2, push it through softmax layer, you predict M. That's what's happening. Oops, what's happening? That's what's happening right here. S1 goes through a linear softmax, predict I. S2 goes through a linear softmax, predict M, so on and so forth. Right, so this is just a repetition. Right, so that's the whole generation part, and we still haven't talked about masked self-attention, so we're going to talk about that as well. So before talking about masked self-attention, we need to understand why we need masked self-attention. So obviously here, for example, let's assume that let's assume that you are here. You have all the words you need, and it's time to predict end of sentence, right? In order to do that, the decoder first goes through a self-attention layer to understand what words have been produced so far by the decoder, right? So because it needs to understand that there was start, I am a student, all of the words produced so far by the decoder to understand that it's now time to predict end of sentence to end the whole process, right? So that's where self-attention comes in. But the problem is that there's a slight problem with just using a vanilla self-attention in order to encourage the decoder to understand what's happened so far, because there's a concept of causality in the decoder side. So which is actually written all here. Oh, before that, encoder decoder attention handles one query at a time. No. So I kind of talk like that again. So like each time start becomes a query, I becomes a query, M becomes a query, student query, not just like I talked about it. I explained that like everything was taking a turn and then going through a for loop. But again, this is not a for loop. As I depicted here, it's just a bunch of matrix operations again. You put all the actually ground truth words, because this is a training phase. During the training phase, we know the ground truth. So we put all French words and all English words input into the encoder and decoder at the same time. So you can calculate this matrix all in a single go, all in a single simultaneously at the same time. You don't need to go through a for loop actually. So no for loop. We already know the input to the decoder, ground truth English sentence. We can process all queries at once, like I said in the attention matrix. But the problem is during training, we do know ground truth English sentence. So that's why we can put all the English sentence in the decoder at once, because we know the truth. We know the answer. We know the true answer translated English, because this is during training. But in the during testing, we don't know the GT English sentence. That's the problem. So there is a discrepancy between training phase and the testing phase, because training phase, we do know the ground truth. So that's why we can calculate encoder decoder attention at the same time. But in the training phase, in the testing phase, we don't know. We just have to start from the start symbol, kind of guess what the next word would be, and then make the prediction, and then take that prediction, put it into the next step, put it in, hopefully predict the right word M, and then get that prediction, take the prediction, and then put it into the next word, into the next position, so on and so forth. So we need to do it auto-regressively. So we need to do a actual for loop when we're testing, because we don't know the entire English sentence. So there comes a discrepancy between the two scenarios. So yeah. We generate one token at a time during training, so we don't know the total length of the output sequence. We don't know when the end of sentence termination symbol would occur. It only depends. Nobody knows. It's only the decoder knows when the end of sentence symbol would occur. So, and we use the previous output token as next input. So we take the output, put it in as a next step input, take the output, put it as a next step input, and we call that an auto-regressive generation. Right, so that's where mask self-attention comes in. So we can't, because of the discrepancy between these two phases, these two training and testing phases, we can't just use vanilla self-attention, because otherwise that would be cheating. So I'm going to explain why that's a cheating. So for example, let's assume that we are here. We have all the French words input to the encoder, and we have R1, R2, R3. And now we already have, well, I actually forgot about the start. So there's start of sentence. Start, we have I have we M we have A. So now let's assume that we are at the time where start IM is given, and it's time to predict A. That's where we are. Then we currently know Jesuit étudiant, which are the French tokens which is given to us. Even during the testing phase, French sentence will be given to us because they are fixed. They are the question being asked to us, right? So we already know all the French tokens, but we only know the the two tokens from the English side. And now it's token to predict. Well, actually, I forgot this SOS here. It's time to predict A. That's where we are, as I said. So let's assume in the encoder's self-attention layer, let's assume that let's look at what Sui, the second token, is doing inside the self-attention. When Sui is the main character, then it can look at itself, it can look at the left, it can look at the right, because in the self-attention layer, the encoder, there's nothing that restricts the word from looking at both sides, right? Including itself. But what would happen if the same rule was applied in the decoder side, decoder's self-attention? For example, decoder knows I am, so I am. All student is unknown. They're unknown. They haven't happened yet. They haven't been predicted yet. And it's M's turn to do a self-attention. So this self-attention is sorry, I'm gonna go way back here. We're looking at what's happening. We're looking at what's happening here for the SWI, and we're looking here for what's happening in M. This we already covered, so this we're not looking. We're not interested in this anymore. We're covering this. Right. So in the self-attention layer, if the same rule is applied to the M, it can look at itself, look at the left, look at the right, look at the right. That is impossible. That is physically impossible because A and student haven't happened yet. They haven't been predicted. So for M, when M is the main character, you cannot look at something that hasn't happened yet. That would be cheating. That would be if you look into the future, that would be cheating, and it wouldn't be allowed in the test phase. During the training phase, this could happen because during the training phase, we do know the entire sentence. So if we could allow this kind of attention, like future attending, to happen, but then the same thing would not be possible during the testing phase. So that is why we disallow it even during the training phase to make the same thing, to apply the same rule during the training phase and the testing phase. So even during the training phase, we don't allow M to look into the future. We can only look to itself or the past to the left. Yeah, this is not allowed. It shouldn't be allowed because this wouldn't be possible anyway during the testing phase. This is okay because even during training and testing doesn't really matter because during the training phase, during the testing phase, French sentence will be given to you as a whole anyway. It's the English sentence that's the problem. So we only allow this to happen. So this is it. What happens in the masked self-attention? We're basically masking. We don't allow this to happen. We're masking them out. So that's why it's called masked self-attention. So in the decoders, masked self-attention, what happens is if you look close enough, the arrow never goes to the future. If you look at student, it can attend to itself, to the left, to the left, to the left. But I can only look at itself. Well, there's hidden SOS actually. Look at itself, but it can never look into the future, right? So the rule is that each token can look at itself or to the left, but never to the right. So that is masked self-attention. So in order to actually make that happen, how should we do it? So you remember the QK transpose suffix, right? So what we don't want is, for example, M giving a positive non-negative attention weight to the future, right? We don't want that to happen. No. So what we do is we manipulate the softmax, we manipulate the QK transpose like this. So there's original QK transpose divided by square root of D. Before applying softmax, we actually multiply some mask that looks like this, which is triangular matrix. Everything below the triangle, everything below the diagonal line is 1. Everything above is negative infinity. So when you multiply them together, then you can imagine everything here would be all dying out because they're all negative negative infinity, and negative infinity put through a softmax gives you a zero score. This one thing to really be careful is this should not be 0. No, 0 will give you a positive softmax output. It should be negative infinity. So this will give you like this. So after you multiply this negative infinity mask to the QK transpose to a softmax, then you will have a new looking attention matrix that looks like this. Everything above the diagonal line is zeroed out. They're all zeros. And everything below the diagonal line is now a proper attention distribution or probability distribution. Still summing up to 1. And then you multiply this new attention matrix with V, the value, then you would get a thing that you really wanted. So I only looking at self, like looking at itself and I, looking at itself and to the left, to looking at itself and to the left, right? So the rule is now is held. Question from 변무현. 만약 포지셔닝 코딩 하지 않고 학습 테스트하게 되면 마스크 셀프 텐션이 그 역할을 해주나요? 좋은 질문이신데요. 포지셔닝 코딩을 빼고도 빼도 마스크 셀프 포텐셜이 있으니까 시퀀스가 지켜지지 않느냐? 사실 그렇지는 않을 겁니다. 왜냐하면 예를 들어서 마스크 포지션 인코딩이 없으면은 어, he 뭐 is a boy, she is a boy 뭐 어쩌고 하면은 아니네. 적절한 그게 아닌데 어, 네, 적절하네요. 네, 적절한 예시네요. 그러니까 he is a boy and 뭐 she is a boy가 걸이죠. she is a girl 뭐 이런 식으로 이제 문장이 있다고 치면은 1, 2, 3, 4, 5, 6, 7, 8, 9 9단어짜리죠. 그러면은 이제 요거를 이제 우리가 제너레이션 하고 싶어요. 예를 들어서 뭐 프렌치로 뭐 있겠죠. 무슨 뭐라고 뭐식이라고 이제 뭐 똑같은 어, 그 불어가 있을 텐데 그걸 넣고 우리가 이제 요걸 빼고 싶은 거예요. 이제 he's a boy and she's a girl이라는 영어를 빼고 싶은 건데 그럼 이제 마스크 셀프 텐션을 해야 되는데 예를 들어서 시점에선 그러면은 얘도 보고 얘 보고 물론 자기도 보고 이렇게 보겠죠. 이렇게 보겠죠. 근데 만약에 포지션 인코딩이 없으면은 요 is랑 요 is는 같은 is예요. 그러면은 얘가 요걸 볼 때랑 얘가 요걸 볼 때는 정확하게 같은 어텐션 웨이트를 가지게 될 거예요. 왜냐하면 QK 트랜스포즈를 생각해 보시면은 이 이즈랑 이 이즈는 같은 포지션 인코딩이 없다면은 똑같은 임베딩을 가지고 타고 들어오기 때문에 QK 트랜스포즈를 하다 보면 똑같은 어텐션 웨이트가 나올 수밖에 없거든요. 근데 그걸 원하진 않잖아요. 우리는 이제 뭔가 이 오더가 있기 때문에 이거랑 뭔가 달라야 될 것 같다는 생각이 있잖아요. 당연히 이 언어를 하는 사람이라면. 그렇기 때문에 포지션 인코딩은 없으면 안 돼요. 마스크 셀프 포텐셜 하더라도. 네, 좋습니다. Right, I think this is it. So this actually ended earlier than I imagined because I was expecting a lot of questions and then there are a lot of contents to cover. So I was expecting maybe spending 5 to 10 minutes more, but actually no. Interesting. Right, so this is it. So this is what happens in the mask self attention. So you've learned mask self attention, which is for the decoder to understand what's happened so far, and then based on that, so actually maybe I just need to draw one more big picture once more. So here in the mask, so there was SOS, I am a student. Here, put into here. After the mass self-attention, you would get a SOS only attending to itself, I attending to itself, and SOS like this, and then you would get the same Z1, Z2, Z3, Z4, Z5, but now these Z's are different from these Z's because in this encoder's self-attention, Z's would be completely mixed left to the right, completely this unrestricted attention. But in the decoder side, mass self-attention, the Z's would be only partially informed. It will only look at the left, never to the right. So that's where your Z's are. And then going through the encoder decoder attention, each Z will become a Q. Z1 will become a Q1. Z2 will become a Q2. Z3 will be Q3, Q4, Q5. And then there will be K's and V's here. So after that, you will have, I'm going to call them Z primes. Z prime 1, Z prime 2, Z3 prime, Z4 prime, Z5 prime, mixed up with all the V's here, V's in K's, based on the compatibility between Z1 and all the K's, all the input words, Z2 and all the input words, Z3 with all the input words, weighted sum with the value, then you would get Z prime 1, Z2 prime, Z3 prime, Z4 prime, 5 prime. Going through the feed-forward network, and then you would everything will be going through a feed-forward network separately, independently, and then you would get R1, S1, S2, S3, S4, S5, and then you do that for there will be 6 encoders. There will be 6 decoders. You repeat this process for 6 times. You get the final S1, S2, S3, S5. You put it through a softmax. you do a negative log likelihood. Out of all the words, 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 you want I, you want M, you want a student, you want a termination symbol. That's it. And then you have 5 loss functions, 5 negative log likelihood functions. You do a back propagation all the way to here, all the way to here. It's just end-to-end product, end-to-end process. And by doing so, you update all the WQ, WK, WVs, and WOs and all the learnable parameters by doing a backprop from here. All right, so this is the end of transformer. Any questions so far? Hopefully, this whole picture is very clear to you. The encoder side, the decoder side, you really must understand to the very details, because we're going to learn BERT and GPT and multimodal learning, and well, after that is graph neural network. I mean, diffusion has nothing to do with transformer, but after that there will come a graph neural network as well, which also is very, very has a strong connection to transformers. So BERT is only the decoder of transformer. GPT is only the decoder of transformer without the encoder decoder attention. So everything is just like a simple modification. All the modern NLP achievements are basically based on transformer with slight modifications to small modules or small techniques. So you should really understand what's happening here. All right, any question before I end? I'm kind of surprised that there's not as many questions so far. I'm going to believe that because that's due to my excellent explanation. All right, I'm going to wait 5 seconds before I end the class. 제가 지금 방금 말했듯이 이게 아마도 이번 학기에서 제일 중요한 강의일 수도 있거든요. 왜냐면 이거 다음에 따라오는 버트, 버트, GPT, 그다음에 요즘 많이 하는 그 달리나 이런 것도 사실 버트 기반으로 버트로부터 이제 그 프롬프트를 이제 이해하고 그걸 이제 디퓨전을 넘겨주는 거기 때문에 이제 그런 것들을 다 이해하시려면은 이 트랜스포머의 그 작동 원리를 명확하게 하셔야 되거든요. 그래서 트랜스포머를 그 바닥부터 구현하실 수 있으면은 제일 좋고요. 나중에 이제 그냥 그 파이토치의 허깅 페이스나 이런 거 쓰는 게 아니라 그냥 파이토치의 아주 기본적인 그 리니어 레이어들만 조합해서도 당연히 얘를 만들 수 있겠죠. 왜냐면 이게 다 리니어 레이어밖에 없으니까. 이제 그런 걸 하실 정도로 이제 익숙해지시면은 좋을 것 같습니다. Alright, I think there are no more questions then. Okay, one final question from 전소영. 마스터 포텐셜은 두 번째 디코드부터 안 쓰는 것이니 두 번째 좋은 질문인데 항상 씁니다. 굉장히 좋은 질문인데. 네. 이게 여기서만 쓸 것 같잖아요. 지금 이 마스크 셀프 포텐셜이 여기에서만 쓰고 여기서는 안 쓸 것 같잖아요. 여기서는 다 씁니다. 항상 매 레이어만, 제가 복부시를 말씀드렸죠. 매 레이어마다 씁니다. 매 레이어마다. 그리고 여기도 사실 뻔뻔한데 포지셔널 인코딩이 있어야 돼요. 얘도. 영어도 당연히 포지셔널 인코딩이 있어야겠죠. 여기가 불어였다면 영어 쪽에서도 당연히 숫자를 그 개념, 이 시퀀스 개념을 넣어줘야 되니까 포지셔널 인코딩 여기도 있고 매 레이어마다 마스크 셀프 다 있습니다. 그러니까 한 번이라도 치팅을 허용하면 안 돼요. 계속해서 치팅을 방지해줘야 됩니다. 매 레이어만. 계속해서 미래 보는 거를 계속 방지를 해줘야 되는 거예요. All right, so I think this is it. If you're interested in the architecture, you should really study. I mean, implementing transformer by yourself is an excellent idea. Also, if you're not really sure what's really happening just based on my explanation or description, you can look at Hugging Face because they're all open source. So you can look at the Hugging Face's transformer implementation and see what happens, because there are some differences between what I explained here, because this is all based on 2017, the original transformer. But since after, a lot of changes has been made to transformer, like, make it more, faster to train, more stable optimization, more, versatility, whatever. So if you're interested, you can closely study Hugging Face library. All right. So thank you very much. This Thursday, it will be obviously transformer practice sessions. So hopefully you pay attention. All right. I'll see you guys next Tuesday. Bye-bye. Thank you.